secondary analysis in modeling. A lot of people do the classical analysis, which we're supposed to find in any model stuff. Classical analysis are basic traditional analysis you should normally carry out on a differential or an initial value problem. Now, an initial value problem is the problem that we formulate to actually describe the system, and you carry out some basic. So we will begin to look at how do we address questions from biology, because mathematical biology is not mathematics alone. That means mathematical biology or mathematical epidemiology has to do with using mathematics tool or using mathematical method to respond to questions in epidemiology, to respond to questions in biology, not in mathematics. Now, if you are going to have any method, maybe like your work is going to be methodical. Maybe you have a new method. It's a different thing. Like somebody, I was trying to look at a work, examine a particular student, and then the whole thing that the student has done is just already made. It's a PhD work, but already made methods. Already made method is not novel. Now, it's not novel because they are already being, somebody developed that during his PhD, and then you are using it. That you are using it does not bring novelty to your work. What brings novelty to your work is that you have propounded some objectives, and then out of those objectives, you are developing a secondary analysis to respond to the question. Not showing me passivity and boundedness. You have not done anything. You can start with that, but you must go from known to the unknown. But a lot of people we see in Nigeria, I can tell you 1,000 paper is one thing. One thing. And that change that paradigm. Trying to see modeling in a much more useful and beneficial way to the community and still maintaining the mathematics. So we are going to show some of these things as we go on here. As the father of modern mathematical epidemiology said, that's Ronald Ross. He even won a Nobel Prize for doing that kind of job. He did the first malaria modeling, even as a medical doctor. So he said, the mathematical method of treatment is really nothing but the application of careful reasoning. Careful reasoning. Now, your maths must go with careful thinking. Now, thinking out of the box. It's not just the math alone. Now, the math, very good. But math from thinking, we give you a good new theorems. Math from thinking will give you a good new quantitative response. Now, if you don't think, that's why he said, mathematical method of treatment is really nothing but the application of careful reasoning to the problems. So if it is just to publish, do you know that in today's mathematical model paper, you don't need to think. You just need to publish anything. You can publish in Elsevier, it doesn't mean. Springer, it doesn't mean anything. A lot of people are doing that, but if you look at the content, it's waste, it's rubbish. I've seen a lot of papers like that. It's rubbish. They are published. That a paper is published does not mean it's completely perfect paper. And you see, this we have seen in many mathematical model papers we have seen in Nigeria, because they are only dealing with one thing. You understand? And then, where are the high burdens of the disease? The population, the demographic heterogeneity of the disease. Because disease also have, there is a way it affects ages. Take for instance, for onchocerciasis. Now, men are more affected than women for onco. So if I don't understand that, it will not inform my model well. Now you must understand which age group does it at the target. So if you see what I'm not going to do as a mathematical modeler or as a mathematician is to every behavior I'm seeing in the biology, what mathematical function can I use to represent it? Do you understand me now? That's where it comes. I'm seeing this kind of behavior, like the student I was trying to address yesterday. So we got to a point and I said, okay, since this disease is a form of sex-structured model, because it affects the men more than the women, so we should be able to look at Who is going to bring the board for me? Because I'm a mathematician, so I have to write something on the board. So mathematics provide a powerful language that forces us to be logically consistent and explicit about assumptions. Now, so I was trying to tell him that now it means that you cannot really model onchocerciasis correctly if you don't capture it according to the biology and the pathogenesis. Now, so I said this is going to be a sex-structured model, because we would like to look at how the disease spread among both the female and the male in the population, so that when the government say that we should provide control interventions, who do we target first? Like in COVID, do you know that COVID, many people are modeling a lot of rubbish in COVID. Do you know why? Because, you see, the problem of mathematicians starts when you don't understand the biology. You just model nonsense. When you don't understand the biology, so what are you doing in the epidemiology space? What are you doing there? So the problem starts, like for COVID in Nigeria, that's why COVID in Nigeria was different from COVID in US or in Britain. Because some of the people I was working with a group then in Oxford, and I was part of the Nigerian COVID-19 modeling group from NCDC. I was part of the national. And then what we did, now we were trying to see, okay, now we said, some of those guys were asking me that, Emmanuel, why is it that Nigeria by now did not collapse? Do you know why? Because they felt like Nigeria is a country that does not have good health facilities. That by now a lot of people will have been in the hospital, and then when they are in the hospital, which facility do you have to take care of them? Given our population. Let me give you an instance. Let's take for instance about in Ondo State. What's the population of Ondo State presently? By projection. Anybody? Do you know? Many of us don't know. You don't follow the story of population. These are things, if you are a scientist, these are things you must search from time to time. The population of Australia should be around 5 billion plus by projection. The last time they did census was 2006, right? So there is always a particular rate of increase by national population census every year. You understand? There is a population projection. So by now, Ondo State should be around 5 million to close to 6 million. Now, take for instance, maybe like 2.5 million of people in Ondo States were infected by a particular disease, maybe COVID. Now, which hospital do we have in Ondo State that will take care of them? Answer me now. Are there medical people here? Nobody. There's no medical person. No medical person here. Oh, they are supposed to be here. So only mathematics people. Which department are you, sir? Mathematics. And you? Public health. But you are public health. You didn't talk. I think the MC will take care of that after now. We would like to know you. So what we are saying is that, so when they were modeling, when COVID was to be modeled, you have to first look at the population. Because modeling has to the population dynamics of the infectious disease. So you are modeling at, now for COVID in Nigeria is different. Transmission dynamics of COVID in Nigeria was different from transmission dynamics of COVID in Britain. Why? Because the age stratification are not the same. Now in Nigeria we have younger people, younger population are more than the senior citizen. People who are in the range of less than 40, 45 years, they are more, maybe like 60%. The population pyramid of Nigeria is different from population pyramid of Britain. It's different. So people who are younger, they are more in the population. People who are younger, they are more in population in Nigeria. People who are older, they are more in population in Britain and in Europe than Nigeria. Are you getting me now? Some of them even became asymptomatic. They were not brought down by the disease. After a few days, they recover and they move on. But people who had underlying disease, which are more in the Western world, some of them have some lower respiratory problem, they have upper respiratory problem, they have some of them have some other underlying sickness that they are battling with. So when COVID comes, what happened? It attacked them, and some of them die. Some who didn't die, they had other like complicated issues like that, like kidney problem and all that. So you find out that in dealing with modeling, you have to understand the demography. For malaria, which group is being affected by malaria most in Nigeria? Plasmodium falciparum, which group? Which population? Under 5. Under 5. Women, pregnant women and under 5. So if you are modeling malaria and you want to really model, you must bring all of this into place. Which function in mathematics is going to respond to that age structure? Are you getting me now? That's what you begin to think about. Can I get functions in math that can use to represent that? So it can be in form of districts or continuous. And if you are using district, you should know the kind of model you use. If you are using continuous, you know whether it's PDE or ODE to capture that system. Are you getting me? So what we are saying is we for that model, we now said, okay, what do we do? Sex structure. So I'm going to have male and female. So I'll develop a model that capture the dynamics of onchocerciasis for the male group, and then the dynamics of onchocerciasis for the female group. And then, because onchocerciasis is being transmitted by black fly, that's Simoleus spp. Now, what happened is a vector-borne disease, and then, but we saw that this particular group, the biology was talking about it, that men are more infected than female. So we want to see, so that when if there's going to be intervention, why should they give focus more to men than women? Because the model will already predict that the male are being infected more than the female. And then the same thing with COVID. Now, at a point when they were to distribute the vaccination, what did they saw? They saw that the senior citizens are being affected more than the younger generation. So they had, for that one is age structured, this one is sex structured, age structured. It means that we have two populations, maybe the younger generation and then the adults. The adults can be ages from 60, maybe greater than 60. This is less than 60. And then I can decide to also make it 3. Maybe less than 60, between 40 and 60, and then less than 40 here, to really see better. So in this one, I'm having 3 age groups. So the model is going to be very huge, because you are dealing with different ages, because you also want to know at the end of the day which age group do I need to deploy vaccination to first, to target, to be able to reduce the morbidity. So we have encountered very interesting and inspiring challenges, discussion at the end of workshops on infectious disease modeling with some questions or some themes that people arrive at, especially when dealing with data. A lot of things have come up. Now, I would not want to waste our time on that. Now, for instance, what do we mean by a case? What do we mean by a case? Who is going to respond to that? What do we mean by a case? Or an index case? Let me put it like that. I want to make it more interactive. What do you mean by an index case? Yes, I think you are from public health space.
this case is an individual who has come down with a particular disease.
Okay. So an index case is having the person must have been diagnosed. You understand? Maybe after showing some symptoms, he's symptomatic, and then he has. So the symptoms, you see now, most time people treat symptoms, but they don't treat the disease, and that's what many of us do with malaria. You know, we are in a malaria endemic region. Some of the time when you feel sick, everything is malaria in Nigeria. So instead of you to go for test, you go and take some. You already know some drug that you take. Some of you say, I'm very used to this particular drug. Once I take it, I will sleep. Now, who told you it's malaria? Because so you are treating symptoms. Some people in those days during COVID, some people had malaria, they thought it's COVID. Some people had COVID, they thought it's malaria, and they were treating malaria until they found themselves down completely, not being able to do anything. So we treat symptoms, and then so we say a case when data from outbreak investigation and surveillance are presented as time series of numbers of cases. Now, there's a difference between records during epidemic and surveillance. Surveillance goes on from time to time, depending on what people want to do, what they want to identify. They are carrying out survey on a particular disease, maybe in a particular cohort for a particular reason and all that, or it could be for days, for months, for years, for weeks. But when it comes to epidemic, it's something that is a short outbreak. And normally, epidemics may come because in a place where there has not been normal record of the disease. Now, maybe the disease is there. Now, don't tell me that COVID is completely out of Nigeria. Don't tell me. Are you hearing me? Don't ever say it. Do you understand? You cannot say that COVID is completely out. The only thing that we have now is that, you know, what has happened? What happened initially? We had this. It went up. It went up. And then it started going down. When it's going down, something has happened. Now, it means that the disease is still there, but it's at a very low level. Are you getting me now? It's still there. It's at a very low level. Now, when epidemic happens, what will happen is that this is where the disease is now. This is February 2026. Now, if anything happens, maybe there is an outbreak, then there is going to be a spike. This is the normal thing we have been seeing. When there is an outbreak, there is going to be a spike. That is different from what we have been seeing before. And that's where the question lies. What is giving this spike? I mean, before now, there was a low of Lassa fever. But at a certain time now, we are beginning to record very high. What is going on? So it means that some bush burning, some of the infected vectors, they have gone to poo-poo on your rice, on your beans, on your gari, and then you are eating it. You are not even washing your hands and all that, and people get infected. Because some people want to eat bushmeat. What is mathematical modeling? Mathematical modeling is an abstract representation of a system based on mathematical terms in order to study the effect of different components and consequently to make predictions. It's an abstract representation of a system, or it's a description of a system, or a description of of a system using mathematical representation or mathematical language. So in order to study, so what you do, you study the effect of different components of that system. The effects of different components of the system, and consequently to make predictions. I'm going to say something, I'm building a foundation, but I'm going to say something about that much more later. Now, there is difference between a model that you use to study the effect of different components and a model that you use to make prediction. They are different though. A model that is to be used to make prediction will be highly complex model because it's going to bring in, consider a lot of features. It's going to be more complex than a model that you are using to study the effect of different components. Right? Now, the development of mathematical model depends on several factors, such as what? data at hand. Now we emphasize this because we are dealing with our community. So my interest after I finished my PhD was to use my maths, not to waste the maths, but to use my maths to affect my country. To use mathematics to affect national problems, global problems, and I am still on that crusade till today. Now, when I finished my PhD, I actually went to Abuja. I didn't have a data. I did my PhD at the University of Ibadan. And I did something on malaria and schistosomiasis. Now, because we saw that there's a particular immune response. And I did the mathematics. I did the TH1 and TH2. Many of you who did biology, if I'm talking now, you think that I study biology. But that's the way. If you really want to do mathematical biology, you must understand biology. You must know biology. If you don't know the biology of what you are doing, then you have not started. You want to come and talk to people who are doing malaria. You don't know malaria, then you are not going to go anywhere. You can't talk about it. Some people who are doing fluid, they say they are doing fluid. The person does not understand the kind of fluid he's even doing. That's the worst about many mathematicians in Nigeria. He's doing fluid. The only thing he can state is just state, okay, governing equation. What is the governing equation? You don't know. That's the problem. The first thing you look is what the area. You say you are doing fluid dynamics with mathematics, but you don't know fluid. So how will you be able to apply the dynamics? So you'll be applying nonsense. So you must be able to understand the biology. And then you'll be able to. So we understood that now if you are treating schistosomiasis, it's not going to be. I studied from the biology. That is not going to be possible when you have malaria and you are treating. If you have malaria, if you have schistosomiasis, we call that condition polyparasitism, where you have more than one or two parasites in your body. We call it polyparasitism. Now it means that you are housing different parasitic disease in your body, and then you are feeling some symptoms of malaria. Let's say you have schisto and you have malaria. You are treating malaria, and then you are treated. You don't say you naturally recover, especially when you are in an endemic region, because the worm is growing from small to middle to high number of worms that will be in your body. They may not easily make you die, but it will affect some areas of your life in terms of the way you think. Your brain will not work very well. The worm has gone to some people. If the worm enter their cornea, it begins to affect their eyes, their seeing. They have visual impairment and all that. So that kind of disease causes a lot of debilitating issues, more than just killing you. So what happened? We now say that the model now gave an expression that if you treat the schistosomiasis with praziquantel first, then it will reduce the effect of malaria in your body, and then the malaria parasite will submit. And that was how I gave my PhD. Now, what I'm telling you is that there are a lot of mathematics you can do to respond to public health problems. But how do you do them is what matters. So we have to have data at hand. You need data, especially when you want to speak to real world problem. If you don't have data, how do you want to speak? Because we use data to make policy. Now, if you have the math, if I do the math alone, I realize that if it is just math alone, I will be enjoying the math by doing all those my qualitative stuff, local stability. I will do the dynamical system. I will do Poincaré Bendixson. I will do flow theory. All those big maths. I'm doing them. We are still doing them, but I don't want to do that alone because the community I'm speaking with don't understand that. So I needed to now shift into what we call quantitative approach. The quantitative approach is the interest of the public health. How do I predict the number of cases given my mathematical model? After doing all those Poincaré Bendixson, after doing local stability, equilibrium, asymptomatic stability and all of that, what else can I do? And that's why we have interest in that. So the hypothesis to be addressed and the experience of the modeler. Now, once model parameters are fitted with experimental data, mathematical model has the capacity to serve as virtual clinical trials to uncover the success and pitfall of treatment as well as vaccines. Now, recent years have seen an increasing trend in the number of publications, both in high-profile journals and more generally that utilize mathematical models. Now, there have been a lot of publications in mathematical models in the recent years. This is associated with an increased understanding of what models can offer in terms of prediction and insight. And then any model can be typically thought of as a conceptual tool that explains how an object or system objects will behave. Are you seeing that? Now, what do we use model to do? Now, all the things that is going on, like COVID is spreading in the environment, the epidemiology, the public health, they don't understand how it's spreading. Now, I'm going to use my model based on the biology, put people in different classes, and then develop the model, and then come to the computer and put it in coding and show you how the disease is spreading in the population, given the graphs. So the graph will begin to show whether it's going up. So if it's going up, everybody's afraid. And that was why when COVID was going up from 1 to 2 to 5,000 to 50,000 to 5 million, what did they say? Everybody should stay where? Stay at home. Stay at home. Why? Because they don't understand the dynamic of the disease as at that time. So they needed to understand. So, and then we don't also have enough biology confidently to approach that disease. So any model can be typically thought of as that. A mathematical model uses the language of mathematics to produce a more refined and precise description of the system. Now, in epidemiology, models allow us to translate between behavior of various scales at various scales, or extrapolate from a known set of conditions to another. Now, with mathematical model, given a data, you can now I know what has been going on in malaria from 2010, assume from 2010 I have the data up to 2024 January or February. Now my model, take for instance, this is what is going on. The data is saying this. Now up till February 2024, the data is saying malaria is going up in Ondo State. Now, but we don't know what will happen in the next 10 years. We don't know because we are still in 2025, right? 2025. So 10 years time is going to be 2035, right? I can use my model to extrapolate from here and given some confidence interval or some credible interval to tell you that this is a likely thing to happen in the next 20 years. It's going to increase. It's going to come up here. My model can predict the next 10 years and can project the next 20 years. What is going to happen? That's the kind of thing we use model to do. Now, as such, models allow us to predict the population level epidemic dynamics from an individual level of knowledge of the epidemiological factors, the long-term behavior from early invasion dynamics, or the impact of vaccination on the spread of infection. Now, models come in a variety of forms, from highly complex models like the jet aircrafts. You know, it's a very complex one. Need a range of experts to create and maintain them, to simple toy models like bicycles, can be easily understood, modified, and adapted. Can you see? So I was talking about the complexity of a model, and then when a model is simple. Now you can build simple model just to understand what is going on. Simple model can capture what is going on, can read the effect of different components on the disease. Simple model can do that. So for a bicycle, it's very easy, right? Very easy to do. But for a jet, a complex, why is it complex? Why is the issue of the jet, why is it complex? Because one, it's going to be flying in the air, and the number of people it's going to take, there are some buoy that can take as much as 5,000 people. Now, if those people should die, maybe the president is there, everybody is there. No, that's a problem. So if you are going to, if you want to, it's a big risk. That one is more risky. The reason is because, you see, in Nigeria, we don't take so many things serious. Even the life of people. The life of human being is not even important. Talk less of a dog. If you go to Western world, if you kill a, you know, I was in one country some few years ago, and I was seeing a cat moving around the road. He saw me, he was just moving like this. I said, in Nigeria, if you see me, you can't try this. You see a cat just look like you like this. I was passing in front of the cat. You were just looking. Very fine cat, looking robust. I said, wow. In my country, you will already be in the pot. Yeah. Somebody want to hunt you. So, you see, that's why the cat in Nigeria, when they see you, naturally they know that we are hostile to them. They run. Why is it that the cat there will not run? Because they know they are in their psychology. It is already written, package, that it is a friendly environment. So the cat there does not run when he sees you. It's normal. He just stay and be looking and, you know. In my house in Oye, in the night, there's a cat that used to move on the roof like this. Recently, I started praying that this cat must die. Because when I'm sleeping, that's where, especially when I come back from the office late in the night and I want to have a sleep, that's when the cat, I say, you must die by fire because I want to sleep. But in an environment where things are working, you know. So in Nigeria, we don't take, like, when it comes to decision, now, people are making a lot of decision with data prediction in other countries. Now, if you are going to fly a plane, you don't just say, you want to fly a plane, a jet, that has not passed through models. You know, like, before a jet can be allowed or be certified, they must have run the model, they have run the simulation, and it has passed through sensitivity test, specificity test. They have to go through a lot of, the model will have passed through model calibration, models, a lot of things before they will now develop the aircraft. All those aircraft you are seeing, they already model it, put it on simulation before they will now build it. So when it passes the sensitivity test, between 90, 99 to 100%. If it doesn't go, then they will not allow that thing to go out. The product will not be launched out. So the same thing, you see, mathematical model is not just applied in biology. There are many areas of application. But our own interest in our center is to use it to solve problems in epidemiology primarily. But there are other areas. People are doing models in other areas, in other countries, in different aspects, engineering and all that. And some in finance. So, now, if you want to, the decision whether to travel by aircraft or to travel by bike depends on several factors. Do you know that? If you want to travel by flight, by bike, or by aircraft, it depends on several factors such as time, distance, and cost. If you want to go from here to Abuja and you want to ride on a bike in Nigeria, you know what it means, right? You want to go with your wife, maybe you newly got wedded, and you want to go and do your honeymoon in Abuja, and you took your newly wedded wife with a bike, and you are going to Abuja. You can be sure before you get to Okene, that wife, especially the children of Gen Z of these days, he will draw before you get to Akure because the roads are very bad, right? Not only that, there's a lot of risk, and then I don't know how long it will take you to get to Abuja. But if you take an aircraft, talking in terms of time, you can gain time, but it will be costly. Am I right? Like from Akure to Abuja should be around 120,000. No. I say tow, not fro. Tow 120, fro 120. That's 240,000. A to and fro is 240. Oh, 200 going from Lagos. You see now. Now it also depends on the aircraft, and also depends on the timing you book. On the timing you book. So now, similarly, which sort of model is the most appropriate depends on the precision or generality required. Right? Which model? Is it a simple model or a complex model do I need? It depends on what? It depends on the precision or generality required, the available data, the time frame in which the results are needed. Now, if you want me to develop a model within 2 weeks to answer a particular problem, then I will have to check those conditions. Do I have the available data? Is this model going to be for prediction? I need to check whether I will also make it a general model that can just answer some few things, because it's not easy to actually develop a complex model within 2 weeks. Now, by definition, all models are wrong, in the sense that even the most complex will make some simplifying assumption. Now, when I say all models are wrong, does not mean that they are not useful. It's a different thing. So, it is therefore difficult to express definitely which model is right. Though, naturally, we are interested in developing models that capture the essential feature of a system. Now, what do I mean by that? If your model does not show the biology, you have missed it. You are modeling malaria, and then you didn't put female anopheles mosquito. Then you say you are modeling malaria. You only put human compartment. Then you are not modeling malaria, because there is a vector, and the vector is female anopheles mosquito. And you only say that, you only talk about the human population. Now then you have missed it. You are not talking about malaria. You are modeling onchocerciasis. You don't talk about black fly. You have missed it. You are modeling what's it called? Schistosomiasis transmission. And you don't talk about Miracidia and Caesaria and then the snails. Then you have missed it. So all those things must feature in your model. By definitions, yeah. So it is therefore, ultimately, we are faced with a rather subjective measure of the usefulness. Can you see now? The usefulness of any model is our focus. How useful is this model? Now, for your model to be useful, it has to have the biological details. Now, why model? Why do we model? We want to plan for outbreaks. In planning for outbreak, we need to model. Because if you take, for instance, now, in our university recently, in our center, we decided to just see how do we use our maths to even solve problem of our environment. So what do? We ask them to give us their data for student enrollment since 2012. And then we got the data, and then we make a forecast or a prediction. Now, in the next 2 years, these are the certain number of students that will come to Foye. The next 1 year, the next 2 years, we should be expecting close to 100,000 students by forecast. If it goes beyond the confidence interval is talking about much more than that in terms of the upper bound. Now, what we are now saying is that the school should make preparation plan. That if 100,000 are going to come in the next 2 years to Foye, what is the plan in terms of the number of lecturers, facilities on ground, accommodation, a lot of things, because the population of students are getting more than the indigenous. So, if not, there's going to be a competition. That's what we call competition in ecology. Competition for a lot of things, social amenities. There's going to be competition in Oye. And when competition starts, what happens? There is going to be survival of the fittest, elimination of the unfit. Some people who are living in that village before, they are going to relocate. The competition will affect the cost of housing, where people live, how much they are going to pay. Now, before, when we came to here in 2012, how much are they paying for house rent? We are paying very, very little amount. Now, to get a room now, because the population is skyrocketing and the competition is getting thicker, now, to get a room, just self-contained, you pay 200,000, 250,000. Now, by 2026, 2027, which we are predicting for them, it's going to be what? It's going to be, maybe it's going to be times 2. Because the population is getting more. So so we said we use it to plan. You plan ahead. So that if you know that this is what I'm expecting, you begin to make space. Then the speed of the spread, it helps you to know the speed of the spread. When we say speed of the spread, you know a velocity time graph, right? That's the way disease spread. You do the disease is going like this. You begin to see as it's skyrocketing, like a velocity time graph. VT with respect to time. And then we also look at severity. How severe is the disease? When the disease is severe, you discover that a lot of people, like normally when the disease is severe, the number of people that will be infected within 1, 2, 3 days will be times 2 of the normal. And then there's no space to keep people. Then, intervention effectiveness. We also use this to plan for intervention effectiveness, evaluate it, and also predict the best intervention. What kind of model do I need? It depends on the question you want to answer. And that is why, if you don't have the question that you want to answer, that is biological to the model, to the disease, then you have not started. Statistical model, it can be statistical, it can be dynamic or mathematical model, or health economic model. I want to move very quickly because now, what are statistical models? They are data driven. They explore correlation and understand the trends and pattern in data. Regressions, talking about relationship between variables. Then time series analysis, which talks about how to identify seasonal patterns, or you identify, beyond that, you can identify a lot of decomposition depending on the kind of time series analysis you are using. You understand? Some are time domain, while some are frequency domain, and some are time and frequency domain, like wavelet. Wavelet is time and frequency, and then we have spectral analysis. We have spectral analysis, which has to do with frequency domain, and then we have ARIMA, which has to do with time domain analysis of the data. Now, used for nowcasting and forecasting to predict the current. So some of those examples we are going to practically see some of the results we have used. There's one we are looking at on MPOS, monkeypox for Nigeria. I think, yeah. So we are looking at that one recently to predict the current epidemiology and where it might be in the next few weeks. Where will the disease be in the next few weeks? You want to know? Time series can help you to do that. Statistical model can also be used to estimate the efficacy and effectiveness of current treatment and prevention measures. Now, but the problem with statistical model is that they are functional. They only deal with surface things, surface things. They cannot actually help you to see the underlying mechanism of how transmission takes place. So we always start with statistical, but we don't end with that. We go into mathematical rigor of mathematical modeling that comes with, because most of the statistical model, time series model, regression model, they are black box. They are black box model. Like machine learning model, they are black box. You cannot do anything to them. You can't change anything. You cannot. But for mathematical model, you can customize. You can develop your model based on your question. It's very dynamic, and they are mechanistic. Now, dynamic model uses mathematical language to describe the underlying biological, behavioral drivers of disease transmission. Mathematical models, once validated against historical data, can be used as tools for scenario analysis. So you can use it to develop various scenarios. The number of cases that will be averted, the number of deaths that will be averted. You want to know the number of people that will die due to the disease, maybe in 10 years' time, if nothing is done. If we bring intervention, what kind of intervention will be the best? We will be able to know that. Then scenario analysis provides evidence to support policy making, allowing the exploration and the comparison of options for intervention against a disease. to support decision. So one of the reasons why we are, like why you need to use data with your model is that because you want to support the decision that is going on in the country. There are a lot of problems in Nigeria that nobody is looking at. Do you understand? Now, and that was why I felt I must not just stay in the abstracts. I need to come to the real world. If I'm the abstract, nobody sees me. I'm just there in the space, in the abstract space. I'm hanging somewhere, maybe in the Ilba space or in the Banach space and all that. And then nobody see me there. I need to bring Banach space to the markets of malaria. Bring Banach space to the market of Lassa fever. Bring Banach space to the market of schistosomiasis. Right? So, and that's the interest. That's why we are showing this now. So, we want to support policy making. Now, by the grace of God, like I told you now, they cannot do anything in disease, especially disease in Nigeria, by the grace of God, and they will not call us. Yes, now, because we are speaking to the problem. That's the way to go. You don't do your maths and stay in your room, do it alone, and then nobody. If I want to do, if it is finance, I want to get to the financial industry, World Bank, and get to solve their problem. Recently, when we are trying to build our building. So the next thing I was thinking about is that now I needed to find a problem that World Bank want to solve. If I solve the problem, I send it to them. Do you understand me now? That's the kind of thing I'm doing now. If I solve the problem, it's either I publish it or I send the problem to them, and then they will call me. When they call me, I present the problem. When I'm able to present the problem, they will start talking. Please, you need to. Then what do you want? I want you to build my center for me. I need fund to build my center. It's when you solve problem or people can talk to you. I was in Swiss doing my postdoc at the University of Basel, and then these people came. Bill and Melinda Gates, they came, and I presented my work. It was from there the journey I am today started. Say, you mean you can do this for Nigeria? Then I can do it. So it's not, if you don't solve any problem, nobody looks at you. Especially real-time problem. There are a lot of problems. Water problem, environmental problem, pollution problem, many problems. There are mathematical modeling of climate, environmental change. What are those going to do? And do you know, we have a lot of mathematical tools to solve those problems. But where are those people that will do it? We don't know the pathway to get it done. So it's not enough to just do a lot of mathematical rigor. There is need for careful reasoning. I don't know. You didn't even give me time when I started. So that was where the problem commenced. So I was just talking. So next time you give me time so that I will put myself in that structure of the time so give me. So that's why I usually go with my phone so that I can check time. And please give me my phone. Just give me, give me 10 minutes more. I'll round up. I'm sorry for taking the time. But next time you give me time, 1 hour, I will spend 1 hour. I tell you, you know me. But you didn't give me any time, so I felt I could just be flowing on. So, yeah. Now, dynamic model simulates. You simulate the process. There are major 2 types of dynamic model. One is deterministic. Deterministic does not capture randomness, stochastic fluctuation. Deterministic. And that's what many people are doing in Nigeria. Deterministic. Right? ODE, ordinary differential equation, is deterministic. Difference equation, deterministic. Partial differential equation, deterministic. Integral differential equation, deterministic. They are all deterministic. Even fractional, integer value differential equation is deterministic. Fractional, they are all deterministic. Now, the limitation of deterministic is that now you cannot be used to capture small population, and especially when the disease has just started. So, because the random fluctuation is going to frustrate it. It's going to frustrate the deterministic effect. So, and that's why, we look at stochastic aspects, stochastic. So, for deterministic, it can help when the population is large population. But the challenge is also that the initial condition is always the same. Everything will still be the same. So, we have a challenge with that. But it's still usable. It's useful. We can use it. Right? But now, stochastic. Now, in the recent time, I'm also doing something stochastic, deterministic. I have a paper, 1 or 2 papers on that. Stochastic, deterministic. When I have a deterministic, I induce some stochastic fluctuation into it to take care, especially some parameters that I discovered that has a lot of, like, take for instance your beta transmission probability. You induce stochasticity on it, it changes everything. So stochastic, it explores outcomes, obtain a distribution of the outcome. Because when we talk about the transmission parameter in the model, transmission is not always like a constant thing. When somebody is going to transmit a disease between one person and the other, it follows a particular probability distribution, which is not exponential. Most times we assume it's exponential in most of our deterministic model. Sometimes it's Poisson. And so if I induce that, then I make my deterministic to stochastic. It carries a stochastic something. And then it can also serve as a stochastic differential equation. So we also have beta population, individual or agent-based model. Right? So district models use whole numbers, rates converted to probabilities. Now there is also a way we can discretize an ordinary differential equation when you want to do meta population. Now, take for instance, I'm talking about location, different locations. I'm capturing the differential equation, and then I want to look at how people are moving from one place to the other. For me now, I stay in Akure, but I come here, maybe mosquito bite me in Akure, and I stay in Ondo overnight. Now, because of staying in Ondo, I've been transmitted with malaria, and then I fell sick here. But the trace was that, now while I'm also here, I've also infected some mosquitoes. While I'm here, maybe like 3 or 4 or 5. Now we also capture that in mathematical model using difference ordinary differential equation. Difference ordinary differential equation. Where you discretize a differential equation, you put it in discrete form. Especially when the locations are many. Then you see the stochastic, you see the behavior of stochastic. Now, what are we trying to do here? We are looking at the number of infected people. But you see, stochastic is giving us in a very wonderful way. Now, it's showing us that, you remove it. Stochastic is showing us that, now, as at day 5, look at what stochastic is showing us. It's showing us that between 0 and 20 people have been infected. Not exactly. Deterministic will say 20 people exactly. But stochastic will tell you between 0, can you see now? Between 0, maybe 0, 1, 2, 3, 4, 5, up to 20. Between 0 and 20, it gives a range. That's the beauty of stochastic. As at day 10, look at it. It gives you between, look at it, I don't know where it's starting here. If you trace it, maybe between 100 and 300 have been infected. As at the 10. So it's giving us a range, in range. Metapopulation is a concept in ecology. Does not originate from epidemiology. But it's a group of population of the same species that live in spatially isolated areas but interact on some level. So metapopulation occurs when different populations live in fragmented habitat but are connected through migration. Like me now, I'm moving. I stay in Akure, but I come here to work. Some of you even stay in Akure, but you come here to work. Mosquito bite you in the night. You came to fall sick in Ondo, and they take you to Ondo Medical Center to go and get treated. So if they trace your movements, where did you sleep at night? They'll be able to know that maybe it was not here that you got actually the infection. It started from Ondo State and from Akure land, Akure town. So, and these are things population movement need to be traced at spatial level. Then we have metapopulation epidemic model. Just to describe it, consists of n patches. Population of each patch is assumed to be homogeneously mixing. They are mixing. similar. They are similar. It is divided into typical epidemiological of SIR. So in this case, I'm having, take for instance, I'm having SIR. This is S, susceptible, infected, recovered. Ondo State. This is Ondo, and then this is people from Edo who are infected, susceptible. IR, Edo, because people commute between Ondo and Edo, and they are getting Lassa fever. And those places in Nigeria, they are high body states for Lassa fever in Nigeria. I need to capture them and see how people are moving in those two states. This is special model. I want to capture it. So I can have more states than this. Maybe up to 10 states. But I'm saying I'm considering these two states to see what is going on within these two states. How the disease is spreading spatially. So it is it is divided into epidemiology of classes of susceptible and all that. So the network model actually track the network of contact between individuals. How people are contacting each other. They are contacting to transmit the disease. Infection can only occur between infected individual and a subset of the total population which they are in contact. We also have the individual-based model. I have 3 minutes more, I'll stop that. So, or agent models, agent-based. So the individual-based model, this track what each individual. This is highly complex model. Highly complex because I have to model, like take for instance, how many of us are in it all? We are what? Maybe we are 1,000, right? So it's computationally intensive. So I'm going to have, instead of this one, I'm going to have, because I want to model each person here. So I'm going to have, this susceptible is going to be S1, S2, S3, S4, up to S1000. And then I have infected. I1, I2, up to I1000. I'm modeling each person. Right? So in the long run, I'm going to have 3,000 compartments. So then you need to analyze that. And then put it on a computer to run to give you the simulation. You can see how people are spreading. So now this allows chance to determine whether. So what do we do here? We put some stochastic into it. Because how people are getting infected is not going to be normal. It's going to be influenced by randomness, uncertainty. Because you cannot say that this person must actually infect this person. It has to be, it can go this way, or this go this way, or this go this way, or go that way. You see, it's not going to be, a lot of uncertainty are going to be put into it. Each agent or important group assign a compartment. Can you see? Each person will have a compartment. So the number of compartments can increase exponentially. Each agent has set of, what is this? Set of status. You can put them in different status, like infected, susceptible, recovered, and all of that. You can put them in different platforms, and then attributes. So rules are set for how agents interact. What's going on? It's not moving again. I have 1 minute more. Stop now. Okay. So we have health economics model, which are used primarily to explore the potential costs. After you have carried out your scenario analysis, the government wants to know. You have told us that particular intervention is going to work. Maybe LLIN and ACT is going to work for a particular local government. That means it's going to be the best. That will reduce the number of cases to 5. Now, the government wants to know how much am I going to spend for this particular thing in that place. They want to know the cost. So for you to do that, you need to use health economics model to see the potential cost effectiveness and benefit of health intervention. Then you see, as a round-off, statistical model, how much complexity do I need? You start from univariate linear. Okay. So, but what happens is, as you go more complex, do you know what happens? There is increasing realism. It becomes more realistic. The work becomes more realistic. But the challenge is there is a decreasing tractability. You can't track them. Right? So the last one, I think maybe I should stop here for now, and then you can listen. We'll still come back here again. Any question?
Right. Thank you so much, Prof, for the very elaborate lecture that has been given. And shortly, we are going to be taking some questions from us. And once we are done with that, we'll go for a tea break after those questions. And then we'll return also after those the tea break to go into some other sessions where we'll really get to put to use some of the things that Prof started talking about. And one of the things you see is that, it's very important that this foundation is laid, because as we go into other sections where these things that is laying the foundation for will be put to use and people will begin to exhibit it, will be taught how to do few things, at least for these 2 days. These are foundations, and you yourself can question. If, for instance, maybe a facilitator comes up out now and is doing something, you can say, oh, but according to what Prof said the other time, you are not following what Prof said, so that nobody, you already have how it should be in your hands. And so that's why we normally feel that it's a very good thing that will set the ball rolling like this. All right, so you have listened to Prof. He has said a lot of things. Some of us are mathematicians. He has punctured some areas. Some of us are not mathematicians. He has opened our eyes to some things. Some have questions, concerns, and the likes. And you want to bring them up. So within 5-10 minutes, let's quickly do that. Let's engage Prof on what he has taught. One of the things we do in our center is to engage. So he has taught. Now you have listened. Now let's engage Prof on what he has taught. So I want to give us, just signify by raising up your hand. I'll give us numbers. But I thank you so much. I already have 1, 2. Any other person? 3. Okay, those 3 people. Media, you will help me, or protocol, you will help me. Thank you so much to pass the mic around.
Thank you, Prof, for the lecture. Please permit me to sit down because of my laptop, so that I will not do mistake to bring down the laptop. Thank you for the lecture, because was it last year you were in my school, last Ostec, and I didn't have much time to sit down because I was part of the accreditation team. So I decided that I must come for this particular one because I need this knowledge for what I want to go and do. I'm a statistician, and from what you have said, it has opened my eyes more. I will ask a question, and I will also give a contribution, which you will expand more. But the question I want to ask is a minor question. We have dynamic model. Sometimes maybe we call it dynamic or compartmental model or mechanical model. I believe they are the same, but if they are not the same, then you throw more light on them. That is compartmental, dynamic, and mechanical models. It's either we are using them interchangeably, or if they are different, you let me know and throw more light on them. But if you are using them interchangeably, then there is no need for further clarification. Then the other aspect I want to say is for every one of us. From what Proverbs said, we need the knowledge of statistics. We need the knowledge of mathematics, even we need the knowledge of computing for us to do well in mathematical biology. Because you can't talk of stochastic modeling of those models without talking of statistics. It's not possible because they are all based on probability. And I discovered that compatible models, compartmental models, we always start with sometimes with logistic or exponential, but these are not the only probability distributions we have. We have a lot of probability distributions, and we even have what we call hybrid distribution, maybe like normal Weibull, exponential normal, gamma Weibull, and so on. Most of these distributions we have developed them, but we have not actually applied them to mathematical modeling. I think going forward we should try to explore some of these industrial distributions and the ones that are combined. I've not seen Weibull, I've not even seen gamma. Most of the ones I see are always exponential, Poisson, logistic. So I think by the time we start exploring all these distributions, then the stochastic aspect of this this modeling will become more realistic. Thank you.
All right, so I'll give the mic to Prof to respond.
Yeah. So we have statistical models which are called functional models, which deals with surface issues, like surface aspect of the problem, like talking about trends, talking about the patterns in the data and observation and all that. But for, like, when you say compartmental model just has to do with the way you dissect the population. You understand? But dynamic model are two. It's either they are deterministic or stochastic. When you say a dynamic model, something dynamic has to do with time, the time scale. So it's either they are deterministic or stochastic. Now, there are deterministic that are discrete, which is difference equation or discrete. So, or there are deterministic that are continuous. Continuous in what? Continuous in time. You understand? Some also continuous in space. So you have to be able to like differentiate some of these things. And then we have stochastic. So dynamic models are two, deterministic and stochastic. But that deterministic, you cannot say deterministic compartmental model. When I say that, what I mean is that now I'm actually using a deterministic model which is based on compartments. In the sense that I'm using, let's take for instance the one I said there, SIR. I divide the population into 3: susceptible, infected, and recovered. But I'm using what? Ordinary differential equation, which is deterministic. Or I'm using PDE, which is deterministic. Or I'm using difference equation, like using Sn plus 1 equals to Sn. Is difference equation or discretize, which is within a limit finite number. So I think that on the other one, we are, when it comes to now the area statistics usually come strongly in mathematical model is in the inference. When you want to look at prediction or you want to estimate parameters, some of those parameters follow a particular or some other ones, so we can subject them like somebody. If I'm going to use a Bayesian approach, you understand, I must have a prior. My prior can follow a particular probability which you have said, either a normal Gaussian or Weibull or anyone, and then from there to the posterior one distribution. So some of us are using it underlyingly, especially for parameter estimation. It's being used very well because that's the area called mathematical statistics. Are you getting me now? So we are using in our center for us to estimate parameters of the model. So that's why we don't shy away from the statistics. I'm still going to talk about that aspect tomorrow on what are the tools, what are those things you need to do mathematical models, and some of the results we have come out with from it. Thank you very much.
So let's have the second person. You can stick with the mic.
Okay.
Thank you so very much. First and foremost, I would like to appreciate our presenter, Professor Bakare E.A., for the enriching presentation I really learned a lot. Also, I also like to appreciate the organizer of this program. In fact, God will continue to bless you. Now, this is my question. Actually, I'm in pure mathematics, but I'm interested in this topic that has to do with infectious disease. Having learned and still about learning more on modeling on infectious disease, Prof. Sir, please, I want to know, how can I possibly bring out a topic when I'm trying to give a kind of research publication on my work that has to do with infectious disease? Because I'm in mathematics. My topic should include mathematics, not like biology, infectious disease. If not, you know, it won't be accepted in my area of work.
Specialization.
Or specialization. My specialization is in functional analysis. We deal with Banach spaces. Prof also mentioned something that has to do with Banach spaces when he was talking. And then he said we should bring Banach spaces to the market of malaria, tuberculosis. So I got interested, but I was like, I want to know, how can we collaborate this Banach space or our various areas to this infectious disease as headline, as topic, so that we can always bring out more research publications in it. And I'm also interested because it gives a lot of pictorial display on graphing. You know, in pure is always abstract. So it will give more interest to people that, yes, this is actually what we are talking about when we talk about pure mathematics in area of functional analysis, fixed point theory, and the likes. And I'm sure that will be applicable to everyone seated here that is in various areas, either in applied mathematics, statistics, and computer, data science as a whole. Thank you.
Is that your question?
Yes, sir.
Okay. Now, mathematical model is a representation in mathematical terms of the real world or real devices. In other words, mathematical modeling of epidemiology, the spread of malaria, let's take for instance, or the spread of tuberculosis. You understand what I'm saying now? Now, what is there? The question is not in mathematics. The question is in the biology. But the method, the tool that I need to answer that question is in what? Mathematics. And that's why we come about mathematical epidemiology or biology or anything you may talk about. Do you understand? Mathematical sciences. Are you getting me now? That means the application or the use of mathematical methods, whether it's functional or it's algebra or it's stochastic or it's differential equation or anything, into how do I use that tool that you say, fixed point, how do I use it here? Now it comes when, now the first thing is, I was talking about the issue of model. How do you come about model? The first thing is that you must understand the biology. If you don't understand the biology, you cannot do the model. You understand? So when you understand the biology, it's from the biology you will create the question. Once you create the question from the biology, you will now bring in what mathematical function can I use to respond to this question in biology. You are a mathematician, so you must be able to now think, because now you are now applying that function and that fixed point. You want to apply it to solve problem. So now I needed to, before you use fixed point, you needed to develop the problem. The problem now is the mathematical model. In what form will the problem come? The problem first now, maybe it's coming as a differential equation, right? Which has to do with rates. Everything we are doing there is first order differential equation. If you have done differential equation. First order, dx1 over dt, dx2 over dt, dx3 over dt. But in this case, I'm changing my dx1 to be x, making it susceptible population. I change my dx2 to be I, making it infected population. I change my dx3 to be R, making it recover. Because those are the kind of people we find in the population. Infectious, we call them non-infectious. We have people in the population who are infected and infectious. People who can infect other people. If you cough now, you can get COVID. Or you get malaria if mosquito bite him or her or something like that. And then people who also recover, we have them in the population. So now, how do I now relate each of these compartments? How do I bring them into play? Now, what do I want to model? Let's take, for instance, the question I have. What's my question? My question, I just have one question now. What is the, okay, let me say, how does COVID-19, or let's say, how does measles spread in Nigeria? Let's take, for instance, how does measles spread in Nigeria? Now, measles, that's a question. That question is not from mass. Do you understand? It's from where? The biologist has asked you, can you help me to see, how can you explain with mass how measles spread in Nigeria? I'll go back to my board. Measles in Nigeria, we have in Nigeria different population. In the population, there are people who are susceptible, who are not infected. They are non-infectious. I have one. This is susceptible. Now, the other one, I have people in the population who are infected. Susceptible, infected, recovered. Now, all of these people, it's possible that if the infected did not die and they remain in the population, they can infect the people who are susceptible. Evil communication, corrupt good. So these infected people can mix with susceptible people. They infect them. Abi? So when they infect them, in mathematics, we say, at what rate will they infect? I call it minus beta IS. Take, for instance, this beta, the rate at which they are infecting, right? Sorry. Right? Beta. This beta is minus. Can you see it's minus? It's minus, Abi? It's minus because now, these people are susceptible before. But now, because of contact with bad people, who are those bad people? The infected. They are the bad people. So he went and contact with them at this rate beta. So he is already infected now. So it means that the population of people who are susceptible is reducing. Are you getting me now? Now, these people will now join the infected class because this guy who is infected has gained one person or two to himself. Right? So this one is a gain, while this is a loss to the susceptible. Right? So in the process of time, some of these susceptible also die naturally. They die naturally. They can die naturally as they grow up. Now, some of these infected can die naturally also. Right? Now, I can also say that over time, some of these infected can be recovered naturally. They can recover. So when they recover, they join the recover class at this rate gamma. This is a simple way we can understand what we are talking about. Now, you have developed this model. The question is, how do I analyze it? Now, this model is not finished. Oh. Now, let's now look. This is an ODE. This is an ODE. Abi? It's an ODE. It's not yet a problem. Do you know it's not yet a problem? In mathematics, it's not yet a problem because it's an ODE. How does it become a problem? Who is going to tell me? Good. Clap for yourself. Are you a lecturer? Eh? Master student. Which school are you? Futa. Okay. Can you show me? Can you put an initial condition here? Let me see. Can you put the initial condition there? Okay, yeah. this initial condition, what's the difference between this one and this one?
That is the population at time zero.
So what is different? Are they different? So you have not really specified. Your initial condition is not well defined. So what should be the initial condition? This is a realistic work. You don't know. Do you agree we don't know? Do you agree you don't know? Because this one is the same as this. You just use another representation. This is the same as this. Is at initials. Yeah. It's the same. The same. You just change the notation. That's what you should do. That's what you should do. Put initial condition like that. If you want to write your model, do you write 500 here? So what do you write normally? If you are going to develop, if you have been developing model, what do you write here? Let me ask. It's S not you write, right? Okay, I'll correct you today. Go and sit down. Now, this is a general initial condition, right? It's general. Now we are talking about a specific problem. This is general. Now, this initial condition may not work for this one because this is a specific problem. It has to do with susceptible, infected, and recovered. So what do I do here? Now, this one is going to be greater than 0, strictly greater than 0. Why? Because when COVID started in 2020, Abi, what was the population of people in Nigeria who does not have COVID? What was the population? If you get it, I'll give you biscuit. What's the population of Nigeria? People who doesn't have COVID in Nigeria. You know, when COVID started, what was the population of Nigeria? Susceptible. You know, nobody has COVID. What was the population of Nigeria? Let's assume, just assume. 250. Can we say 250 is equal to 0? What do we say? 0. That's how a mathematical thinks. Applied mathematician. It's greater than 0, strictly greater than 0. Right? So for this one, for I of 0, what should we put there? Yes? Let me see your hand if you are saying greater than or equal to 0. Your hand up above your head, oh. Yes, greater. People who knows it well, greater than, yes, greater than or equal to 0. Yes. Wait. Greater than or equal. See where mathematics comes. Now, if I infected, if it is equal to 0, listen, oh, if it is equal to 0 initially, what will happen here? Yeah, there will not be transmission. There will not be transmission. So it cannot be equal to 0. It's going to be what? Greater than at the initial. It means transmission did not happen. So it's not going to be a nonlinear differential equation. So for it to be nonlinear, it has to be greater than 0, strictly greater than 0 at the beginning. Then R, recovered. Recovered is going to be what?
Greater than or equal to.
People are quick right now. Because I don't change I. Yeah. It can be greater than or equal to 0. Because you don't, at the initial time, you know how people are recovered. So, let me tell you, if you are doing a mathematical model and this is not correct, you are only deceiving people. You know that? Even though you are published, you are a dangerous person. Do you know nobody can follow your decision because this initial condition of this solution, the uniqueness of this solution to be unique. For the solution to be unique, the initial condition must be well defined. Do you understand me now? If it's not well defined, there's a problem. Do you understand me now? So if your initial condition is not well defined, then you can't talk about uniqueness of the solution. So when you have done this justice to this, Mama, who they ask for analysis, right? Now that's when we now talk about, when you say analysis of the model. Can you help me clean this side? The analysis of the model, everything. Don't clean the analysis. So you have done the model. You have developed the model. The model is well defined. It's fine. It's okay. Then you have to talk about two things goes on in analysis of the model. The first one is the qualitative. I'm going to talk deeply on this tomorrow. Qualitative analysis. Qualitative. What do I call it? Qualitative. Now, under the qualitative, it's not quantitative, qualitative. Under this qualitative, you have many things. Now, the fixed point you are talking about, Mama, you can do fixed point here. Because this is already a dynamical system, right? So you can study the qualitative behavior by using maybe existence, and uniqueness. You can do existence and uniqueness of this problem. You can do existence and asymptotic stability. Asymptotic stability. You can go on to do local and stability in the large. Local stability and stability in the large, which is called global stability. Stability in the large or global stability. Right? You can do bifurcation, right? And central limit theory. Central limit theory. Central limit theory. Right? You didn't know that? They didn't teach you that? Central limit theory. Bifurcation. Either forward bifurcation, up bifurcation, limit cycles, backward bifurcation, and then you can go down again and do stronger dynamical system theory. And then for that, you do Poincaré, especially for a planar system. Poincaré, Berdiksen. Berdiksen theorem, that's 1, 2. You can carry out, especially if it's an oscillation. If it's an oscillation, and then you are looking at periodicity, seasonality. You look at Floquet theory. Floquet theory. And Poincaré. And then you go further to look at other stability theory as well. Stability theory. You look at, okay, I'm not talking about equilibrium. You also look at equilibrium here. Equilibrium, which has to do with fixed points. When you set each of those equations to 0, then you look at perturbation. You understand? Perturbation. When you perturb the system, then you can find the local stability as well. You perturb the system, you find the local stability, because some are going to be linear and some are going to be non-linear. Then you take out the linearity aspect and you find the eigenvalues. And then with that, you can decide whether your equilibrium is stable or non-stable, or is asymptotically stable, local stability. And then you can look at chaos theory. You can look at chaos theory. And there are a lot of theorems under chaos theory that you can look at. That is, how does measles spread, Abi, in Nigeria? So what now? Do you know that if you have done all this one, they are just classical? I'm going to talk deep about that. They are classical. They are not your own results. If you do positivity, you do boundedness, you do invariant region, they are not your results. They are not your own. Those are basic analysis you're supposed to do for any mathematical model. It's not your result. That does not make your work to be novel. Now, you now go back to your question. Now, coming back to this question now, you see that I'm talking about how does measles spread. Now, can you tell me one particular parameter here that is responsible for the spread of measles? No, I chose many parameters. One parameter. Who is going to tell me? One parameter that is responsible for the spread in this model. That's where your secondary analysis will start. One parameter that is responsible. Yes? If that parameter is not there, that can't be the spread. Better, right? The contact. I mean, that guy is in chemistry. He's thinking. This guy is thinking. Can you clap for him? He's thinking well. He's thinking. You see now, Do you know that many mathematicians don't know how to think? That's why physicists are applying our maths very well, better than us. Mathematician, you know how to cram. You don't know how to think. Reasoning is more important than the mathematical rigor, especially to solve application problem. So you must engage in thinking. Mathematicians are always cramming theorems. When you don't understand the theorem yourself, stop cramming theorems. Start thinking the theorem. When you start thinking the theorem, you will produce your own theorem. The man that produces theorem, he thought about it. He didn't cram it. If he's cramming it, he will produce the same thing now, and nothing is changing. So, it's beta, right? So this beta, you are going to build a theorem around it. So that's where the main thing, this is the meat of the work. If you can build a theorem around this beta, the first way to build a theorem around this beta is to first do the geometry. Do you understand? What do I mean by geometry? The graph. Graph. When you look at the graph, what beta give you in this particular model, you develop. So that's why we talk about topology. Do you understand? Now, when you understand the topology of a particular parameter, you can develop its theorem. Do you understand? The topology is the geometry. That's the graph. Once you put up the graph and you show this, then you can find a lot of things around here. In fact, I can change this parameter. Once I change, once the behavior is giving me, it will make me to develop a theorem for this, and then I can prove it. And that's a secondary analysis. Are you getting me now? You can use Banach space, you can use anything. Thank you. Okay, so the other one is quantitative. So I'm going to talk about that one much more tomorrow. Quantitative aspects, which has to do with the interests of the public health people, which we also are interested in. Quantitative aspects, talking about how many cases are we going to have in the next 10 years for monkeypox. We have some prediction that we did on monkeypox on our work recently. Maybe Mogojuri will show some few things. The paper will be published. We want to use it to inform policy for NCDC. Paper should be published very soon, by the grace of God. So you can predict in the next 2 years what will happen, how many number of cases are we going to record, how many people are going to die. If government did not do anything, how many people are going to lose their life? So these are things you can use. So I think.
All right, thank you so much, Prof. Okay, the last person.
Thank you, sir. Surprisingly, I wrote down 2 questions. The first one was answered when Prof was responding to the questions, the question from the first person. And surprisingly, again, the second question has to do with where the question used to emanate from, not from mathematics. He has actually cleared that. But let me just add this. Can I say this, that deterministic model produces a more reliable projection than a stochastic model? Can I say something like that?
Yeah, well, it depends on the population you are looking at. Now, for large population, that is what we call the law of large numbers. Like for small population, stochastic, especially when an epidemic just started, stochastic is very good. It will give you just like the graph I showed the other time now. It gives you a very good prediction. But when the population is becoming large, too large, there's what we call LLN, law of large numbers. It's weakening the power of stochasticity. So at that point, the stochastic will become deterministic. So, like talking about the way malaria is now in Nigeria, it's enormous. You can't use stochastic to capture, but you can flavor your deterministic with some stochastic fluctuation, just like the one I said before. that you can reduce stochasticity to a deterministic model, and then it become it has some stochastic flavor. You understand? But normally a stochastic model captures well than a deterministic model for a small population, or when a disease has just started. Is better than a deterministic model. You understand? So those are the things. But deterministic model is good when you are looking at large number, because what happens is that everything will be the same. We will give an initial condition. After some time, it will still, because of that deterministic nature, it doesn't take care of randomness. It's likely to give you the same. Do you understand? So that's the battle we have with deterministic. So what you can now do to help deterministic is to flavor it with some stochastic fluctuation, and then it boosts that randomness into it, and then so I think that's the idea. Thank you.
All right, thank you so much. Please let's put our hands together for Prof. Okay, it's a very good one. We're starting this way. And before we go for our tea break, please, I want to say to us that for those of us that have not registered, please ensure that you register. And then if you want to use the convenience, and for male and female, we have them here, so you can use them. Before we go, we'd like to know us. Please, we do that very quickly. You pass the mic around, just shortly, your name and where you are from, and then what you are doing. Maybe if you are a lecturer, you are a student, you are whatsoever you are doing currently. So you let us know, like your area of interest. All right, so let's quickly pass the mic, and then we do self-introduction, because going forward, we want to know who our audience are, and then we'll be able to interact with you better. All right, so you can start from there. Yeah.
Thank you so much. My name is Dr. Ihai Abioye from UNIMED, yeah? And from Mathematics and Computer Science departments. Then my area is the mathematical modeling.
All right, you are welcome, sir. Next person. You may sit down because we understand the nature of the chairs.
Well done, sir. My name is Shinyobade Folasha Adebolanle. I'm a student of UNIMED, Department of Mathematics and Biological Mathematics.
Level of students? What level of studentship?
Okay, PhD student.
Okay, great. Which area?
Biological mathematics.
Yeah?
Mathematical biology.
Okay. Comma.
Thank you very much. I'm Dr. A. Akisumade. I'm a lecturer in the Department of Mathematical Science and Computer Science. And my area of specialization is optimization and modeling.
Optimization and modeling. Thank you so much. You are welcome.
All right. I'm Nwana Ewan Onyebuchi. I'm a PhD student with Icammda. Thank you very much.
Please don't forget to mention your area.
Good afternoon. My name is Dolapo Onielu, a PhD student, Computer Science Department on Modeling and Data Analytics.
My name is Ronke Olonfemi. I'm a mathematics student. My interest is in mathematical modeling of infectious disease. Thank you.
All right, next person.
I'm Dr. Deborah Daniel. I'm a postdoc scientist at Icammda. My interest is in mathematical modeling of infectious diseases.
All right, thank you. Next person.
My name is Gabriel Orudepo. I'm a lecturer in the Department of Chemistry, University of Medical Sciences, Ondo. My area of research is physical chemistry.
You are welcome. Thank you, sir.
I'm Abisola Babatokpe from Health Information Management Department, University of Medical Science.
We can hear most of us. We are not using our mics.
I am Abisola Babatokpe from Health Information Management Department, University of Medical Sciences. My area of interest is disease surveillance.
All right. Thank you.
I'm Oyetunde Oyeyemi from Department of Biosciences and Biotechnology. I'm a parasitologist.
We're happy to have you, sir. Thank you.
My name is Daniel Muyiwa Adevisoye, master student at Federal University of Ekiti. I'm also at International Center for Applied Mathematical Modeling and Data Analytics, Ekiti. My area of interest is mathematical modeling for infectious diseases. Thank you.
All right, thank you so much. Please let's come from the back.
My name is Hope Daiko, a master student in University of Medical Science, and my area is mathematical biology.
Mathematical biology, all right.
I am Oluwaseun Mugojuri. I'm a PhD scholar at Icammda FUI. My background is in mathematics, and I'm using mathematical modeling to study the transmission dynamics of malaria in Nigeria.
All right, thank you. Okay.
Mr. Kafo, one Peter from Futa. My area of interest is solid mechanics.
Solid mechanics. All right, thank you so much.
I'm Olawole Alaba. I'm a microbiologist. Also, I'm a physics scholar at Icammda. Thank you.
Microbiologist, thank you so much. It's good having you. Next person.
Okay. My name is Stella Kayode. I'm a molecular biologist.
Molecular biologist.
Department of Bioscience and Biotechnology, University of Medical Sciences.
All right. It's great having you.
My name is Tajudeen Oreade. I'm a PhD student. Infectious disease, parasite immunology.
Infectious disease?
Yes.
Modeling, right?
No, not modeling.
Okay, infectious disease generally. Okay, all right.
Thank you. Yeah, good afternoon, everyone.
Yeah.
My name is Hafiz Abidemi. I'm a postdoctoral scientist at Icammda, and I'm also a lecturer at Federal University of Technology, Akure. My current research is focusing on modeling the effect of vaccination and seasonal malaria chemoprevention on the transmission dynamics of Plasmodium falciparum in Nigeria. Thank you.
You are welcome, sir.
My name is Dr. Ogmudele from Department of Physics, University of Medical Physics. I'm into Earth and Environmental Physics.
Earth and Environmental Physics. You are welcome, sir. Next person.
My name is Dr. Solani Kiabola. I'm a graduate intern at Icammda, and my area of specialization is modeling and data analysis.
Modeling and analytics. All right, thank you.
My name is Dr. Adele Yetolulokwe from Nigeria Maritime University. My area of specialization is dynamics of structure.
Dynamics of structure. Thank you. You are welcome.
My name is Alabika Azimolu Hashim. I'm an intern at International Center for Applied Mathematical Modeling and Data Analysis. My area of specialization is mathematical modeling and data analysis.
All right, thank you. It's great having you.
My name is Opayinka Messi Oluwafumlayo. I am an intern at Icammda, and my area of specialization is data analytics and mathematical modeling.
All right, thank you.
My name is Mrs. Raji Sunwa Adedoyin from the Department of Mathematics, Lagos State University of Education, LASWED in Lagos. I'm also a PhD student in Lagos State University, LASU. My area of specialization is fixed point theory.
Okay, fixed point theory. It's great.
My name is Matthew Eko. I did my PhD at University of Lagos. I specialize in mathematical statistics.
Okay.
What we do, we develop probability distributions that are not in existence to model every aspect of life. Currently, I'm a lecturer in the Department of Mathematical Sciences, Lagos State University of Science and Technology, LASOSTEC, the University of Excellence.
Thank you so much. It's great having you, sir.
My name is Gabriel Ogban, University of Cross River State. Also a student in FOIE, working with Professor Bakari on CSM.
Okay, it's great having you. Thank you so much.
My name is Arawande Jacob Olalekan, a lecturer in the Department of Science, Laboratory Technology, and I specialize in analytical food chemistry.
All right, thank you. It's great having you. So the last over there.
Yes. Okay. My name is Dr. Adigboro Oluwashemire.
from Department of Mathematical and Computer Science, UNIMED here. My option is in numerical analysis.
Numerical analysis. Okay, it's great having you.
My name is Ogumola Oyilola. I work as a scientific officer with the Ondo State Primary Health Care Board, and I'm a PhD student in the School of Public Health.
Okay, thank
My
you.
interest is in infectious disease modeling.
All right, it's great having you.
My name is Okunlola Oluyemi Adewale. I'm a special statistician, and I specialize in infectious disease modeling and mapping using Bayesian archaical model.
Okay, Bayesian and mathematical model. Thank you.
My name is Okunbe Gideon. I'm from Mathematical Computer Science UNIMED. My area of specialization is blockchain technology.
I can't get you, sir.
My area of specialization blockchain technology.
Blockchain. Okay. Blockchain technology.
I'm Samsi Babafemi, a master student at Federal University, Oye Ekiti.
Thank you. My name is Olalekan Adebimpe. I'm a professor of public health and clinical epidemiologist. So my area of specialization is in infectious disease epidemiology. I want to thank you for coming. Thank you very much.
We are happy to have you, Prof. Thank you so much, sir.
Hey, good afternoon, everyone. My name is Abdulatif Valideje. I'm a graduate intern at International Center for Applied Mathematical Modeling and Data Analytics, Icammda at Federal University of Oye Ekiti. And my area of specialization is infectious disease modeling and data analytics.
All right, thank you so much. Next person.
My name is Basirat Olawumi Lakimade. I'm a PhD student at the University of KwaZulu-Natal. My area of research is fixed point theory and optimization. I'm currently a visiting scholar. Fixed point theory and optimization.
Okay, fixed point, all right.
I'm currently a visiting scholar at Icammda.
All right.
I'm Lawal Abdulatif Olawale, also from University of KwaZulu-Natal, South Africa, optimization, and I'm a prospective PhD student willing to switch into mathematical modeling of infectious disease.
All right, great.
Also, I'm a visiting scholar at Icammda.
All right, great having you, sir.
Yeah, thank you, sir. My name is Fatokun John. I'm a lecturer at Caleb University of Mathematics, Computer Science, and I specialize in mathematical modeling and optimization.
Mathematical modeling and optimization. Thank you, sir.
Thank you. My name is Michael Ajishope from Federal University, Oye Ekiti. I specialize in function analysis, so I'm looking into how I'll merge functional with modeling.
All right, it's great having you, sir.
My name is Imodu Michael. I'm a graduate intern and NYC corps member at Icammda, and my specialization is in applied mathematics, mathematical modeling of infectious diseases.
All right, thank you for coming.
My name is Yanolu Edungbola, and I'm a graduate of University of Ilorin. My interest is forest economics.
Forest
economics.
Economics. All right. Thank you.
I'm Dr. Famutimi in the Department of Mathematics and Computer Science, a lecturer there. I'm into data science and machine learning.
Okay. Data science and machine learning. You're welcome, sir.
I am a DBC MTMU, Academic Staff, Department of Biosciences and Biotechnology, University of Medical Sciences, Ondo. I'm a food safety and environmental health expert.
Wow. You're welcome, sir.
I am Ibitola Dejumo. I'm a computer scientist. I'm into cybersecurity and machine learning.
Okay, cybersecurity and machine learning.
I'm Dr. K.A. Daudo from the Federal University of Technology, Akure. I specialize in optimization and mathematical biology.
Okay.
My interest is actually to look into the modeling of maybe infectious and non-communicable diseases involving delay in the system or in the intervention. Thank you.
You're welcome, sir.
Yeah.
My name is Josiah Oji from the Federal University of Technology, Akure, Mathematical Science Department. My specialization is mathematical biology.
Mathematical biology. You are welcome.
Dr. Gumboyo Femi. I'm from Applied and Biostatistics, University of Medical Sciences, Ondo. I'm also a fellow of Nigerian Malaria Modeling Fellowship. Thank you.
You're welcome, sir.
Yes, I'm Dr. Lumuyiwa James Peter, lecturer at UNIMED. My research area is in infectious disease modeling and data science.
My name is Akinbulo Sayemi, a master's student from University of Medical Sciences, and I specialize in mathematical biology.
All right, you are welcome, sir.
My name is Balog John Tebitokbe from the Department of Mathematical and Computer Sciences, UNIMED. So my area is in applied statistics.
All right, thank you. It's great having you, sir.
Dr. O. Olanega from Federal Polytechnic Ilology. My area of specialization is numerical analysis.
You are welcome, sir. Okay, so we are going to the last column there.
My name is Agbaje Wilson. I'm a 300 level medicine student.
Okay.
My name is Cholulope Oshitoko. I lecture in the Department of Biostatistics, Applied and Biostatistics, School of Public Health here in UNIMED as a biostatistician. Thank you.
You are welcome, ma.
I'm Dr. Adedayo David Adeniyi. I'm a software engineer. I specialize in artificial intelligence, machine learning with application in security and health-related issues.
Wow, it's great having you, sir.
I am Kosoko Segun, lecturer, Maths and Computer Department, UNIMED, also a PhD student at Federal University, Oyo Ekiti.
Thank you.
Area of interest is modeling of infectious diseases.
All right, it's great having you.
Adeosun Olajide is my name. Department of Maths and Computer, UNIMED here. Major area is AI, artificial intelligence.
Artificial intelligence.
Where the sub-area is complex system.
All right, thank you so much, everyone. It's great.
Okay, myself. Yeah, okay, my name is Olagbami Oluwafemi Samson. So I'm a master's scholar at Icammda FUE. So my area of interest is infectious disease modeling. Thank you. Okay.
I am Akiyemi Festus Akinsuyi Baini. I am a postgraduate student, Department of Community Medicine, Ondo State University of Medical Science. Thank you.
You are welcome, sir. Olashupo Idowu Isaac is my name. I'm a PhD scholar at Icammda, and my area of specialization is in mathematical modeling of infectious diseases. Thank you. And I don't think I have to introduce Prof again. You already know Prof. Okay, so let's go out and have our tea break. And then we will be returning by 12. Sorry? We'll be returning by 5 minutes past 2. We'll return by 5 minutes past 2. Yeah, so we have about 20 minutes to stretch and interact with people. This is a time to network. This is a time to meet new people. While you are taking your tea break, please meet with people and then try to register. And I'm aware that some of us may not like the tea in the break. Just take the break and leave the tea for me. All right, thank you. So let's go out and